Welcome to another episode of Mr. Bell's online notes at home. Today we're talking about isotopes and a bunch of fun stuff about atoms and how to calculate numbers of subatomic particles. So let's get started. The first vocab word for this section is atomic number. An atomic number, which is sometimes used as a letter, capital Z, is the number of protons in the nucleus. All atoms of the same element will have the same number of the protons and thus the same atomic number. So the atomic number is kind of like the fingerprint of an element. If an atom has 6 protons, it's always carbon. And you can always know that. And so if 2 atoms are of the same element, they have the same protons and the same atomic number. And then to calculate electrons, since most atoms are neutral and not charged, then the number of protons is the number of electrons. Okay, next is mass number. Mass number, which is capital A, is the total number of protons and neutrons in the nucleus of an atom. And so the number of neutrons in the nucleus can then be found by subtracting the mass number from the atomic number, because the mass number is the total protons and neutrons, and the atomic number is just protons. I know where to find all this stuff. So here we have an example of a little element that you'd see on your periodic table. You have the element name, and if we look, oh look, there's atomic number. And so that 42, that's the atomic number. That means that's how many protons are in the nucleus of molybdenum. It's 42. So here's our example for carbon 14. Now 14 is the mass number. So how many protons are in the nucleus? Well, first I'm going to look over here. Carbon, the atomic number right here is 6. So it means there are, boom, 6 protons in the nucleus. So now the second question is, how many neutrons are in the nucleus? Well, over here it says mass number is 14, and that's total protons and neutrons. So it's going to be 14 minus 6 protons equals 8 neutrons. Check, we're good. Then the last question says, how many electrons are in the electron cloud? Well, there are 6 protons, so we know that it's neutral, and so there are also going to be 6 electrons, because protons and electrons are generally the same number unless charged. Here's example number 2. Unknown element has a mass number of 121. So if this element has 71 neutrons, how many protons are there? Okay, well, mass number is neutrons and protons, right? So 121 minus 71 equals 50. 50 protons. How many electrons does it have? Same as the protons, so it's going to be 50. And then what element is it? Well, if you look in a periodic table and look up 50, it's 10, or Sn. So scientists soon discovered that there's these things called isotopes, and they realized, well, there's 2 types of carbon, and this carbon, they all react differently and they act differently, but they're both carbon. They both have 6 protons. And so eventually it found out that isotopes are atoms of the same element that have different masses because they have different numbers of neutrons in the nucleus. And that comes from iso, meaning the same. And so it means it's the same element, but they have different numbers of neutrons. So here's an example. There are 3 types of hydrogen. And you have protium, deuterium, and tritium. And so in protium, which is normal hydrogen, you have 1 proton, 0 neutrons, and 1 electron. In deuterium, you have 1 proton, 1 neutron, and 1 electron. And then in tritium, you have 1 proton, 2 neutrons, and 1 electron. Now calling it protium, deuterium, and tritium is actually, we don't normally do that. All 3 of these are hydrogen, but since we actually come across this a lot in science, we gave them separate names even though they're not different elements. All 3 are hydrogen, but one has no neutrons, deuterium has 1 neutron, and tritium has 2 neutrons. So what stays the same in an isotope? The number of protons and the chemical properties stay the same. So protium, deuterium, and tritium in hydrogen all behave like hydrogen. You can make water with all three. They act just like normal hydrogen. They just weigh a little bit more. Okay? The difference is that they have different number of neutrons. They have a different mass number because they have more neutrons. And as relative abundances, which means you might find more of one and less of the other. For example, on Earth, you find a lot more normal hydrogen, protium, than any of the other two kinds. The other two kinds are usually man-made. So here's another example. You have two isotopes, carbon-12 and carbon-13. Carbon-12, both carbon-12 and 13 have 6 protons each. And you can find that from a periodic table. Electrons, they both have 6 because they're both neutral. But neutrons, carbon-12 has 6 and carbon-13 has 7. So when you're writing out isotopes, you have two options. One is the name method, and that's just element dash the mass number. So that's what we mean when we say carbon-14 and uranium-235. That means carbon-14 that has a total mass number, which means both protons and neutrons are 14. Uranium-235 means the total proton and neutron is 235. The second option you have is the isotopic symbol, and that is the symbol with the mass number in the top left corner and the atomic number in the bottom left corner. So carbon-14 is written with carbon with the 14 in the top left, that's the mass number, and then the atomic number 6 is down here. And then uranium-235 would be written with 235 in the top left, and 92, which is the atomic number, written in the bottom left. So, that wasn't supposed to happen. There we go. Determine the number of protons, neutrons, and electrons in each of the following atoms. Chlorine-27 and uranium-238. So pause this video, work these out, and then when you're done, click play, and we'll go over them. Okay, hopefully you actually work those problems instead of just continuing on. And here it is. So chlorine-27, if you look up chlorine in a periodic table, chlorine is 17, and so it has 17 protons, 17 electrons, and then the neutrons, you take 27 minus 17, and you get 10. Simple enough. Uranium-238, it has everything right there. No need to go to the periodic table. You know that the atomic number is 92, so protons are 92, electrons are 92, and the neutrons, 238 minus 92 equals 146 neutrons. So something you might notice is that as you get higher up into the elements, chlorine is only number 17, you have very few neutrons. So chlorine has 17 protons and only 10 neutrons. But when you get up into the higher elements, you have 92 protons and then 146 neutrons. So the bigger elements, as you get higher up, start gaining a lot and a lot and a lot more neutrons. So some of you are probably wondering, what the heck is this guy for? This guy right here, atomic mass. You always see that little number at the bottom, and now gonna know what it's for and how to calculate it. It's actually called an average mass. So we have relative mass and average mass. Relative atomic masses basically is people decided that the actual masses of atoms are so small that we use what's called a relative mass. If you remember the chart that you saw on Monday or Tuesday, the weight of most electrons and protons are in the times 10 to the minus 27 range. So instead of having to write that all the time, we just define arbitrarily a AMU, or atomic mass unit, to be 1 proton, basically. So carbon-12 has 12 atomic mass units because, remember, neutrons and protons weigh the same. So 1 atomic mass unit is 1/12 the mass of a carbon-12 atom. So a proton has 1 AMU, a neutron has 1 AMU, and then remember, electrons are so small that we pretend that they're 0. Okay, average atomic mass. So when you calculate average atomic mass, basically, since there are so many different isotopes of elements, when you see the mass on the periodic table, that is a weighted average of all isotopes in the universe for that element. So this is the weight that you actually see on the periodic table. It's a weighted average of all the masses of all the different isotopes for that one element. So here's how you calculate average atomic mass. It's equal to the abundance, or what percentage in the universe it is, times how much it weighs, the AMU, plus the next isotope's abundance in percent times it's how much it weighs in AMUs, and then you add them all together and then you get the total. So, for example, copper has two naturally occurring isotopes. Copper 63, which occurs in 69.17% of the universe, and copper 65, which occurs in 30.83%. That means that of all copper, 69% is copper 63 and 30% is copper 65. So you want to calculate the average atomic mass of copper if the relative mass of the isotopes are copper 63, which is 62.94 AMU, and copper 65, which is technically 64.93. So this is how you'd calculate it out. First, I take, again, the abundance percent. So here's the abundance percent, 69.17, change it to a decimal, so 0.6917, times the AMU, and here's the AMU right here, which I got right here, plus here's the next one's abundance, 30.83, 0.3083, and then this AMU, and that's that guy's AMU right there. You multiply this, you add them together, and then you get 43.74 AMU. Remember, units is AMU, and you might notice that there are 4 significant figures in all my numbers, and so I left 4 in my answer. So yes, significant figures is coming back. So this is just like your grades. Oh, there we go. Oh, well, now he's getting bigger. Okay. Ernest Rutherford, if he went to high school and he had grades, normally in your grades you have a weighted average. So what that means is I tell you, well, your daily work is 20% of your grade. Your lab, it's another 20%. And your test, 60%. That's just like saying carbon 12 is 20%, carbon 14 is 20%, and carbon 13 is 60%. Okay, and then if this was his grade, let's say he made a 55 average on his daily grades, not very good, but he did 99 on his labs and 100 on his test. Okay, so you'd multiply 55 times 0.2, and that gives you 11. Then you do 99 times 0.2, that gives you 19.8. 100 times 0.6 gives you 60. And when you add all those up, you get 90.8, which is what he would see on his report card. Awesome. Good job, Rutherford. So when you're calculating these, just think, it's just like when you calculate grades. That's all you're doing. So here's an example. Work this on your own. Pause the video, try it out, and then press play to continue on. Okay, so we're determining the average atomic mass of silicon. We have 3 isotopes, 28, 29, and 30. We have their mass in AMU, and we have the relative abundance, and these are percentages, even though it didn't say that on there. So the first step, I'm going to convert my percentages into decimals. Oh, boom. 0.9221, 0.0470, and 0.0390. Next, I'm going to multiply each line. AMU by percentage, this by percentage, this by percentage, right? And then you get this times that equals 25.8, this times that equals 1.36, and then this times that equals 1.17. Last step, add them all up. Bing, 2.83 AMU. So, go over this, practice finding atomic mass, practice finding the mass numbers, practice determining the average atomic mass of elements, and then we will do a lab when you come to class. And now your notes are finished. So have a good night, and I will see you in class.